everyone, my name is Kilian, and I will be teaching you about the polar plane. So we already know about the Cartesian coordinates, but today we're going to go over polar coordinates. Polar is different from Cartesian, so there are some things that you'll need to know. On a polar plane, we know that we have a pole, which is our center point, which is synonymous to the origin on the Cartesian graph, and then we have our polar axis, which is synonymous to the x-axis. We're going to begin by plotting points. We're going to plot r comma theta, which is going to be your new x comma y. Our first point is 3 pi over 2. So, first we are going to start with theta. Pi over 2 is going to be a positive angle, so you're starting with standard position and you're rotating this way. So now you know that pi over 2 is that 90-degree angle, so we're right here. And the r value is 3, so you're going to count up from the pole 3. 1, 2, 3. That's our point A. Then we're going to do point B. When you have a negative r value, it means that you find wherever theta is, which we already did. It's that 90-degree or pi over 2, which is right here. And then negative is opposite the pole. So we're going to go down 3. 1, 2, 3. That is point B. Next we have point C. This has a negative theta. That means we're going to go in the negative direction, which is clockwise, instead of counterclockwise like the positive direction. Negative pi over 2 is a negative 90 degrees, and once again, the value is a positive 3, so we're going to count 1, 2, 3 from the pole, and that is our point C. Unlike the Cartesian coordinate, these points, C and B, are the exact same point, but can be written in different ways. Every point on your polar graph can actually be written in an infinity amount of ways. Next, we're going to talk about some special curves that happen on our polar graph. So the first thing we're going to do is r equals 4 cosine theta. So what does cosine look like on this type of graph? We know on our Cartesian that it looked like this. It started up at 1, right? And then it got to 0, -1, back up to 1. Now, we are going to take the coefficient of cosine and use that as our diameter. This is actually a circle, which is our first classic curve. So, cosine is a circle that lies on a horizontal line. So this is a horizontal axis, of course, unless theta is translated, which it is not in this case. So we're going to start at the pole, move out 1, 2, 3, 4, and create our circle. Our diameter is 4 because of the coefficient, and we moved outward this way because it is a positive coefficient. Now, what if it was negative? Let's say we had r equals -6 cosine theta. That means it would go in the other direction, but again, it would still be horizontal. So we start at the pole, we go out 1, 2, 3, 4, 5, 6, and we make our circle, and that is our second graph. Now, what about if we have sine? If we have r equals 2 sine theta, it is going to go in the vertical direction on the polar graph. We know when we look at our Cartesian plane that it looks like this, right? We start at 0, go up to -1, 0, back, and then to 0, right? So if we're going to do this, this is once again going to be the diameter of our circle. So we go up 1, 2, because it is vertical. So that means that it looks like this. Now if it is a negative coefficient, we have r equals -5 sine theta. So now we're going down, -1, 2, 3, 4, 5. So both are vertical circles because of where their points lie, and it shows the diameter through its coefficient. Now what if we have more interesting, let's say, curves? We're going to talk about a limacone. So a limacone is spelled like that, and when we add a different variable to the beginning or end of these equations, we get a different picture. So the first one is a cardioid, and a cardioid looks like a heart. So because we know that a cardioid looks like a heart, we identify it as A over B equals 1 or A equals B. So an example of that would be R equals 2 plus 2 sine theta. So it's going to look like a heart. We're going to make our table of values. That's the easiest way to plot. We're going to do theta and R. And so you can go ahead and do this on your own. What are the values of R for these values? You should get 6, 3, 0, and 3. Excuse me. I meant to say 2, 4, 2, and 0. Tricked you, didn't I? Anyway, we're going to plot those. So we have 0, 2, 1, 2. We have pi over 2, 4, 1, 2, 3, 4. And then we have 2, and we have 0. Now I said that it's going to look like a heart because this is going to look like an upside down heart. And that's what our cardioid is going to look like. If we have a cosine cardioid, it's going to go in the opposite direction. So it's going to look something like that. Now, of course, that's me eyeballing it. But that's what our cardioid is going to look like. The next classic curve I'm going to go through is the one-loop lemmasome. The one-loop lemmasome is very similar to the cardioid, except for the fact that it has what's called a dimple, which means it has a little indent instead of making that V that we saw here with the hearts. So, so we identify our lemmasome when 1 is less than A over B, which is less than 2. So it should be in between those two numbers. So an example of that is going to be R equals 3 minus 2 sine theta. We identify that as a one-loop lemmasome. Once again, you are going to do your table of values for this, and you are going to get the following answers. You should have 3, 1, 3, and 5. So, what does that look like? Well, we have 0, 3, 1, 2, 3. We have 1, 1, 2, 3, 1, 2, 3, 4, 5. And like I said, it's going to have a little dimple, so it's going to look something like this. So these are all sort of circles that have been affected in some way. And it looks very much like a cardioid, except it doesn't have such an intense dip there. This area here is what we call the dimple on the one-loop lemmasome. Next, we have what is called an inner loop lemmasome. So a lemmasome with an inner loop means that A is less than B. So that's how we would identify it. Now, this is because when you will get an R value that's negative. And like we said when we were plotting points, you go across the pole. And that's why we get this strange inner loop. I'll show you what I mean. So if R equals 2 plus 3 cosine theta, then we're going to do our table of values, right? So we got, and you see how I've been using numbers in my table of values that are easy to work with. That way you can find exact answers that will plot with R. So you should have gotten 5, 2, -1, and 2. Now notice the negative R value. That is what makes this an inner loop lemmasome. And so what it's going to look like is you're going to have 0, 5, 1, 2, 3, 4, 5. Then we have 2, and then we have this -1. So even though we're coming out on this angle, which is pi, we're actually going backwards. So we're going to -1, and then we're doing 2, and it's going to look something like that. And that is your inner loop lemmasome, and see how it has that loop that goes through it, which identifies it as such. Next, we're going to talk about two more. We're going to do the polar rose. So the polar rose has a parent graph that is written as r equals a cosine n theta, or r equals a sine n theta. Now, n is a coefficient on our theta, so now it's not going to be a circle like the previous ones have been similar to. This is actually going to look something like this. It has petals coming off of it, right? Now, this example that I showed you here was an example with an odd number of petals. So if you have an odd number of petals, that means that n is an odd number. So when n, the coefficient on theta, is even, you're going to have 2n number of petals on your graph. So if it is an even coefficient, you're going to have double that amount number of petals on your graph. However, like I said before, when n is odd, you are going to have n number of petals on your graph. So that one is legitimate, that whatever the coefficient is, that is how many petals will be on that graph. The next thing that we're going to talk about is a lemniscate. So a lemniscate is something that vaguely reminds us of an infinity sign. So a lemniscate is going to be a little bit different because it starts with r squared, which equals a squared cosine 2 theta. Or it could also be r squared equals a squared sine 2 theta. So these parent graphs are really what identify them as their shape. And so, if you had a shape that looked like this, you would identify that as r squared equals negative a squared sine 2 theta. Because when it's on this sort of diagonal, it's a negative sign lemniscate. However, if it's going in this direction, like that, we have r squared equals a squared sine 2 theta. That would be the positive way that you would show a lemniscate. Now cosine, if it was negative, if we had r squared equals negative a squared cosine 2 theta, then it's going to look something like this. It's going to be a vertical infinity sign. And then finally, if we had a positive coefficient, it would be, that's positive, cosine 2 theta, it would be a horizontal infinity. Great. The final thing that we're going to graph today are lines. So lines appear when you have cosecant and secant. So r equals cosecant theta. That graph is a horizontal line, just like that. Now, if we have r equals secant of theta, you're going to get a vertical line, and that is going to look something like this. The only way that these vertical or horizontal lines are going to be moving is if we're translating theta and we're moving it or rotating it. However, these are what these are going to look like all on their own. Finally, the last thing we're going to do is we're going to go over symmetry tests. If you aren't looking at the graph of one of these examples, then you may not know where it is symmetrical. So there are symmetry tests in which you can use to find where they are symmetrical. So we are going to begin with a lemmasome. A lemniscate. and it is a positive cosine lemniscate. So what we just went over was that that will be a horizontal infinity sign, correct? So it's going to look something like that. So say we want to find its symmetry about the polar axis, which we said is synonymous to the x-axis on a Cartesian plane. So a horizontal line, is it symmetric? Well, when we look at the graph, yes, we know it is. However, if we want to do it algebraically, you're going to replace theta with negative theta. And if it still equals the original equation, you know that it is symmetric about the polar axis. So, if we have 2 negative theta, what is going to happen? Well, cosine is an even function, and so that means that this negative sign is not a factor. They actually equal one another, which means that this can be rewritten just as the original equation. So yes, it is symmetric about the polar axis. Now, what about the pole? What if we want to know if it is symmetric about the pole? Well, we are going to replace r with negative r. So, let's do that. Let's say negative r squared equals 2 cosine 2 theta. Well, we know that a negative times negative is a positive, so we're still going to end up with the same equation that we had previously. So yes, the lemniscate shown above is symmetric with the pole, or what was once called the origin with the Cartesian plane, with the pole. Now, what about if we wanted to know if it was symmetric about pi over 2? Pi over 2 is going to be that vertical line. So we are going to replace theta with negative theta, and we are going to replace r with negative r. Now, if we do that, we're going to have negative r squared equals 9 cosine 2 negative theta. Once again, this becomes r squared, and we have an even function, so that negative sign is not necessary. Therefore, this is indeed symmetric about pi over 2. Thank you all so much for watching. I hope you learned a bunch about the polar